Radi, do you hear me? How are you feeling?
Hello, can you hear me?
Yes, we can. Perfect. How are
Okay.
you? Congratulations on your latest awards. Can you share a little bit what you're currently working on before you start your talk? It would be interesting. This is something that I'm encouraging everybody in the audience to do and share the things that they're passionate about currently and the projects that they're working on. So
Yeah,
please, Radi.
thank you so much. I'm currently working in the field of machine learning. That's something that really interests me, and I've been tackling machine learning for the past 2 years. For those who don't know me in general, I'm programming since I was 9 years old, and I tend uh, to want to create products which are helpful to everyone. I founded the AutoML initiative, and I worked on it for the past year and a half. And currently, I'm also working on another side project, which also involves machine learning and AutoML and time series forecasting for trying to predict how the crypto markets are moving, which is something really interesting.
Also interested in crypto. Yeah,
Yeah,
I suppose that this is something that everybody is currently very, very passionate about and tracking where it's headed. Yeah. For example, I myself I plan to start a course about NFTs. It's something that's it's really interesting to me, and I'm an art person myself, so it sounds like something interesting to me. Maybe somebody that has experience with that could share a bit more, but maybe we can create a crypto table as well in the networking session.
yeah, it
So
will be interesting to have a crypto table in the networking.
okay, I can do during your talk. And now we don't have more time, and I on time this for this conference at least. And Radi, please try to share. Okay, great.
All
We
right,
can see
can you
your
see it?
screen. Yeah.
Okay, so
Good luck.
thank you. And do you see the full screen actually? Okay, so thanks once again, and thanks to everyone who is part of DevFest 2021. It's a pleasure to be one of the speakers this year. And for those who don't know me, I'm Radustin Chuvakov. I've already introduced what I'm currently working on and what I'm passionate about. So today I will try to explain to you what AutoML is actually. And because this is a topic which really interests me, but before I jumped into that topic, there were a lot of misconceptions about what AutoML is. And I think that many of you may also have some observations on this. So to begin with, I think there are three main points of view for what automated machine learning is. And the first one is of the average person. So we've all seen these articles in the media which tell us about artificial intelligence, which is able to build better artificial intelligence. And they usually present the information in a way in which people think that this is some kind of magic and that there are some evil robots that can recreate themselves better than we can. And for now, it's not actually the case. There's also the point of view of people which are familiar with technology, tech people, but who don't actually work with machine learning. And they may be software engineers or web developers, and they probably deal with platforms such as Google Cloud, AWS, and then they usually see those advertisements of their AutoML products, such as Vertex AI, AWS AutoML, or some more specialized platforms such as MonkeyLearn and so on. And those people tend to think that AutoML is some kind of interface in which you upload some images and the platform automatically labels them, or you upload some table data and the platform automatically parses that for you. And they are partially right, because that is what commercial AutoML platforms are like. And then the third point of view is from people which actually work with machine learning and people who build machine learning algorithms themselves. They are usually writing algorithms such as linear regression, logistic regression, or deep neural networks. And they know that to build a model that actually works, you have to make sure a lot of the moving parts are aligned correctly, like, for example, the learning rate, the regularization parameters, how many hidden layers a neural network has. And they are familiar with tools which can automate this for them, such as scikit-learn, auto-scikit-learn, AutoGluon, H2O, AutoML, AdaNet, NNI, and so on. We'll take a look at some of them today. So the traditional machine learning pipeline usually starts with some data. We collect some data either from the internet or from some sensors, IoT devices, etc. And the data which comes from the environment around us is usually non-present in the correct way. So we may do some data cleaning to parse data into the right format and to throw out irrelevant or wrong parts of the data. And also at this stage, we may try to guess what the data is actually suitable for. And to do this, we had to pre-processing and feature selection, feature construction. So let's imagine that we are building a model for house price predictions. Usually, no one will care a lot of the middle name of the previous owner when buying a house, right? But they will certainly take into account how many bedrooms the house has, or how many kitchens, or how many bathrooms, and so on. So we can safely remove the name of the owner of the house from the dataset, but we will certainly embrace the information about the rooms we have. And that is feature selection. Feature construction, on the other hand, is creating new features from the existing data. So for those who are familiar with ML algorithms, you know that usually when doing linear regression, for example, you may introduce more features which are polynomial features. So then your model can fit more sophisticated functions. And then once the features of the data and the data we want to fit to our model is selected, we head to the model selection phase. And here we actually have to, first of all, choose what architecture we need to use, because we may have unstructured data and we need a clustering algorithm for that, like k-nearest neighbor. Or we may need to do classification, regression. We may want to use some simple models such as linear regression, as I mentioned, or we may want something more advanced, such as deep neural networks. And also, just choosing one of them isn't sufficient. We also have to build it, right? Because if we have a neural network, then we should select its layers and how they are connected and how many of them we have, and so on. And once the model selection is done, we usually optimize it. So if we have a neural network, we may tune how the dropout and regularization layers work. Or if we have a k-nearest neighbor clustering algorithm, we may fine-tune how much the k is, and so on. In all of these architectures, we have a lot of moving parts that we need to fine-tune in order to the model to work and to work performantly. And to evaluate how performantly the model is working, we usually do some model validation, whether that's calculating the loss, the accuracy, precision, recall, F-score, and so on. And sometimes after we've done all of that, we may have a better idea how to select the features, or now we have the idea of adding more features. Then we should start from the beginning, then go through this pipeline once again, and we find if we find that the updated architecture works better at the model validation phase, it's great for us because we've discovered a better model, right? So the main objective of AutoML is to automate this for us. So AutoML takes some of these or all of these stages of the ML pipeline and provides us with tools that we can use to reuse some of our past findings and to automatically search a lot of different model types, a lot of different parameters, and to fine tune them correctly. So let's take a look, for example, into model selection. Even if we already have determined what type of architecture we want to use, there's still a long way ahead. Like, let's say we really love neural networks. And okay, we'll be searching through neural networks, but we may need a convolutional neural network for image processing or a recurrent neural network for time series forecasting, incorporating long short-term memory. Or we may want to incorporate some attention mechanisms, like those introduced in the Attention is All You Need paper for doing text processing, sequence-to-sequence problem solving. And in some cases, we need both of these things, or we need to combine layers and techniques from different types of models in order our architecture to work well. So the way we select the neural network is one thing, and then how the specific neural network is constructed is another thing. For example, if we have image data, we obviously may choose a convolutional neural network. But then how many layers do it have? Or what actually those layers are and what shape of the data we should fit to those layers. And here comes the neural architecture search. So neural architecture search essentially takes the process of humans manually tweaking the neural network and automates this process. So we may have a neural network which is linear, and we want just to find the different layers of that architecture, or we may want to do something more sophisticated, like how those layers may be reconnected to other parts of the neural network, so it becomes more performant. And for this neural architecture search, we have three main phases. The search space, the search strategy, and the performance estimation strategy. So the search space defines actually what we are looking for. For example, I may only search among fully connected neural networks between 2 and 7 layers deep, and with maximum of, let's say, 20 neurons for each. And defining this search space manually sometimes is a downside or disadvantage because it introduces certain level of human bias. But yeah, we certainly need to know what we are actually looking for. And then we may have some other ways of defining our search space, such as some skip connections. When we are doing neural architecture search, we may have parts of the neural network which we want to disable, and then re-evaluate the model to see if without those parts, the model is still performant, or we want to reconnect the certain layer to another layer to see if this improves the performance. And To do this, we need some search strategy because our search space may be huge. We may have a ton of different ways to construct a neural network, right? We may have thousands and even millions of ways to assemble the model. And the search strategy allows us to find the desired model more quickly. Because let's say if we have random search and we randomly go through different variants of our model and just evaluate them, then go to the next one, evaluate it, this will be really time consuming. And we need some more advanced optimization, such as Bayesian optimization or even reinforcement learning, where when you find some good structure of the model, the agents who look for that structure are rewarded. And if they stumble upon a layers of the network which are just useless, they will be punished for that. And they will more quickly learn which variants are actually more performant than others, and they will skip some of the completely useless variants of the model, and thus saving us time. And also we have some other evolutionary methods and gradient-based methods to look through our search space and try to determine which is the best model architecture we are looking for. So here on the right, you can see an animation which shows how the AutoNet AutoML, which is based on TensorFlow and built by Google, how it adaptively is growing and assembles the different layers of the neural network. And in each iteration, it measures the was for each candidate and selects the best one to move into the next generation. And as you can see here, it iteratively, when it finds some good fit, a layer which fits to the model well, it continues with itself and then adds more on top of it. So this way, it finds the better and better models more quickly than just randomly searching into the space. And then we have the performance estimation strategy, which I mentioned. For certain generated model architectures, we want to evaluate how they perform. And we can just split our data into training and testing sets, as machine learning engineers usually do, and then just train the whole model on the whole training data, and then evaluate that model on the test data and extract some metric like error, accuracy, and so on. And then compare all the models this way. For every new architecture that the search algorithm finds, we will then fit the whole model to the whole data and then evaluate it. But as you can guess, this usually may take a lot of time because we have a lot of different model variations. And as we mentioned, some of them are actually completely useless. So fitting the whole data to all the models will be way too time consuming. And for that, we have different ways for improving our performance estimation. So we can quickly estimate how different models perform and move on to the next to compare them. We have those lower fidelity estimates, such as training and testing on the subset of the data and not on the whole data set. Downsampling the data. For example, if we are working with images or video or sound data, we may downsample it. We may use images with lower resolution, so the computations are quicker, or we may use videos with less frames per second. So again, the computations are quicker. And also we may do fewer training epochs. instead of training the whole model for a lot of epochs to see how the model is performing at the end, we will train for a small number of epochs, which of course will give lower overall performance if compared to training on a lot of epochs. But if all of the models are trained on the same amount of epochs, we may for our comparisons between the different models. And some other techniques include learning curve extrapolation. So if you are familiar with what a learning curve is, here you see how the accuracy of the model grows with time. Epochs is the time the model was training. So learning curve extrapolation, what it does is we stop the training at the beginning with a low number of epochs, and then we try to forecast how this model would have performed with more number of epochs. And this extrapolation is done with some mathematical, statistical model, time series forecasting model. So here, as you can see on this example, we've stopped training at 25 epochs, and then we, in this black lines, we try to guess how the accuracy would have changed if we trained for 120 epochs, for example. And then we use these metrics to actually compare the different models we generated. Okay, and let's actually discuss what are some of the advantages of automated machine learning and why it is so talked about and so muchly hyped. So first of all, it bridges the skill gaps. There is an increasing demand across a wide range of applications for ML engineers, data scientists with skills that businesses often find difficult to fill. And AutoML addresses this skill gap. It makes building and serving ML models easy by automating some of the time-consuming steps in a ML pipeline, regardless of some of the specific skills of the people. So it also improves scalability. This enables someone to devote more time to business problems rather than iterative modeling tasks. For example, instead of you fine-tuning the model and you trying to guess which hyperparameter set is the best for your model, you can just throw your model to a AutoML tool for it to fine-tune it, and you will focus your time on something more sophisticated. And this way, actually, the AutoML pipeline is seen as a productivity tool. And it, of course, saves time. I've been to a lot of online events and conferences about AutoML, and people there tend to think about AutoML as a productivity tool. And they don't think AutoML will replace data science or machine learning engineers, at least for now, in the next 10 years, for example. So just like when Python came out, it was a higher level language, which under the hood does a lot of things that a lower level programmer should do by hand, or the same way how tools such as Keras, TensorFlow, PyTorch, and so on, those frameworks provide us with already already built layers for our machine learning models, so we don't have to implement them from scratch. And this way, the machine learning environment and ecosystem actually grow really quickly because we had a lot of tools which helped us to be more productive, and AutoML is seen as one of these productivity boosts for the machine learning ecosystem. And finally, I wanted to demonstrate to you some machine learning platforms and how actually a AutoML pipeline might look like. So I will show you NNI. This is a framework, open source framework, which I think is backed by Microsoft, and I am using it in some of my projects. So I will take a quick look at it, and then I will also take a quick look at what Google Cloud offers for commercial users. So let me open NNI. And before the talk, I started a experiment in NNI, so I will show it to you. For those of you who are not familiar, MNIST is a data set with a lot of images of handwritten digits. So we have a lot of handwritten digits, and the objective for this data set is to actually classify what each image is. Here is some of sample data of the MNIST data set, and here we have an example of a machine learning model which tries to fit to the MNIST dataset and to predict a newly unseen image, which number it actually is. And here we have this model built in PyTorch. We have some convolutional layers, some linear layers at the end. And one of the objectives which AutoML might handle for us, even though we have built this model by hand, we may want to actually fine-tune its parameters. For example, the learning rate, how quickly it learns. We may want to vary the hidden layer size for the convolutional parts of the network. And what I can do now is go to NNI and head to the trials detail here and hyperparameter tuning. And here you can see that while I was talking in the background, my framework was running different variations of my model with different hyperparameters. So it ran the model with different batch sizes of 128, 64, 32 batch size, with different hidden size, with different learning rates, and with different momentum. And here we can see the default metric I had, how it varied based on the different compositions of the model. So let's say that this default metric was actually the mean squared error, right? And I wanted to minimize it. So as you can see, this green line here actually is the lowest value we got for our metric. So probably if we wanted to minimize this metric, probably this set of hyperparameters is the best one for us. And we may specify in our configuration for NNI, do we want actually to minimize or maximize the metric? And we define the metrics ourselves. So this may be precision, recall, F-score, accuracy, and so on. And here you can see that we have a lot of different trials. I think I ran this one with random search, so I didn't use any optimization here. And as you can see, we had a lot of models which ended up with the same final metric, which if we used some kind of optimization, as I have already mentioned, it would be it would have find this final and best metric really more quickly. And also, this was the hyperparameter tuning part of AutoML. For this model, what we also may want to do is to actually let the AutoML pipeline find the desired layers of our neural network for us. And as I've already mentioned about neural architecture search, we can automate this process. For example, here I have the same model, but on some of its layers, we have multiple variants. So we may have this convolutional 5x5 layer or this convolutional 3x3. And then down the line, we have some more layers which may vary. And when we run this in NNI, it will go through all the different combinations of those layers and show us which architecture performed very very well, which was the best one. And also another metric which you can track with AutoML tools is actually the duration, or how much time it took the model to be trained, because you may find a model which is really good at predicting your objective, but the model may be also really slow. And you hear, based on this information, how much time it took to train, you can evaluate, is it worth it for you to have higher accuracy model with higher training time, for example, or testing time. And finally, something about the AutoML pipeline, which the traditional pipeline doesn't have, is model compression. When running some AutoML platform, which handles the model neural architecture search, the hyperparameter optimization for you, you may end up with a lot of models, as we've already seen, which work well, or a lot of models which are useless. So the model compression phase of a AutoML pipeline is the final phase in which all the models which are found during the testing phase are compressed into one, so we can use them in the end. I don't know how much time I've left, but since we are at DevFest, I would encourage you to take a look at Google Cloud's AutoML. It is more higher level, so you can use Vertex AI and Cloud AutoML without actually having those skills for building the models yourselves. But if you do, you can actually upload TensorFlow models to AutoML and then let it optimize them for you. So if you have some crazy idea about building a app which, for example, classifies images, or classifies video content, or text translation, or whatever, but you don't have the machine learning skills, probably Google Cloud AutoML will have you covered, because its interface is really user-friendly, and it doesn't require all the skills needed to build a machine learning model by yourself. So I think 30 minutes are in. Thank you for your attention. You can follow me on GitHub and Twitter to see more of my work and the projects I am currently working on. And I will be happy if you have any questions.
Thank you, Radi. Once again, quite impressive. Yes, please. Can you all the attendees that were here for Radi's session, please feel free to ask any questions you might have. He's very, very ambitious and intelligent young professional who will be more than willing to answer all of your inquiries. So, Radi, I might have a question. So, have you picked your favorite technology yet? Or you're still exploring the pool of programming languages, and you still don't have like a favorite one?
Well, because I've spent a lot of time doing web development before I headed to machine learning, I have a lot of bias towards JavaScript. And even though a lot of people don't like JavaScript, JavaScript is kind of my favorite programming language. But for now, I am mostly using Python because of my interest towards machine learning. And certainly, I'm continuing to search through the pool of technologies, as you said, because it's really interesting to me how much things you can build with all of these different technologies.
Would you say that and actually machine learning are the future in terms of what the future holds actually for these technologies? Do you think that a lot of things will change?
Yeah, I think that machine learning and automation will certainly transform the way we see the world. Um, as I've mentioned in the presentation as well, this won't happen at one night. It will take some time, but at the end, probably machine learning will automate a lot of our daily lives.
What do you think about the latest project and this transformation that Facebook and Zuckerberg did? What do you think about Meta?
I was expecting it. When I firstly heard of smart glasses, and that was a long time ago. Firstly, Google introduced some glasses. I don't remember how they were called. They were way too early, but this idea of having a meta world and a virtual world is not new. It's from those days when smart glasses were firstly thought of. So I expected Facebook or some of the other big tech to introduce this, and I wasn't surprised when I saw it. But also, I don't quite feel like I will be happy in this virtual world. Uh, I don't know. When I am because I'm spending a lot of time in the internet. I certainly think the internet is something great, but I prefer when being with another humans to be in person. So yeah.
Okay, wow. Thank you. We have a couple of more questions. So we have, do you think AutoML will draw more attention in the near future compared to the rest of the ML disciplines?
Um, so AutoML will first of all will be the productivity tool of all the future machine learning engineers, and also it will allow a lot of people that are not actually dealing with machine learning to start dealing with it. So a lot of companies and a lot of research groups are working actively on AutoML, and from what I've heard, yeah, there's a lot of investments and a lot of time spent by researchers and by companies uh, to continue to develop more and more sophisticated AutoML tools. Uh, and a fun fact I can share with you is that in recent days, I've explored the GPT-3 model by OpenAI. It is actually a language model based on transformers, but they have some really interesting demos in which they having you describe what you want, and then the GPT-3 model automatically builds the code for that in React.js, which is something really futuristic, and this will allow more people which are not familiar with machine learning to try it. I will embrace people to go to the hangout rooms after that, and I can show some demos of it.
Yeah, I will share a little bit more about the tables in a bit. And just one more question we have from Angel. I have a question to Radi. Do you think that many of the ML algorithms feel like redundant? Most people today focus mainly on neural networks.
It's true that a lot of people focus on neural networks, and but that's with everything. Like people always focus on the things that are hyped, and this doesn't automatically mean that the more traditional ways are redundant. Some of them are for specific problems, but not for all. And if you ask the professional ML ecosystem for that, they will answer you that there's no perfect machine learning architecture for every problem. So the specific problems require specific solutions, and for some problems, the traditional algorithms are still relevant and still a lot helpful to you to know them.
Perfect. Well, thank you, Radi, so much for your talk and joining us once again today for DevFest. It's really amazing to grow into the tech ecosystem and all these amazing things that you're already doing. I've already shared in the general chat links to all the networking tables. And whoever is actually joining there and feeling lonely, just indicate it in the chat, and so that other people may join you, and where you can talk to one another and share stuff about the technologies that you're passionate about. Now it is time for a lunch break, so we will give you 1 hour to grab some food, maybe after it grab some beer as well, and come back for the Google Cloud Platform workshop with Jay Campbell. He's a site reliability engineer at Google, and he has a vast experience in Google Cloud technologies. And what else can I share? Yeah, it's going to be in the workshop stage. There I've shared some important links for the beginning of the workshop. Yes, if there are any questions, please, or comments about how you're feeling, if you have any technical issues with the platform, please indicate it either in the chat or write us in Facebook or the emails that we have on our platform. We're here to help. Once again, I would like the most active people in the Q&As will receive some cool swag from us. And yeah, this is it for now. Thank you, Radi, once again. And
For having me.
Of course, always. Looking forward to next year with more interesting projects from your side. And yeah, you're always welcome on the stage of GGG Sofia.
Have a great DevFest from me.
Yeah, thank you. Okay, so I will be